Hey everybody, and welcome back to I Hate Chemical Engineering. This is the fourth episode, or the third, I guess, episode in the series on thermodynamics, in particular Thermo 1. This episode's going to kind of finish out the thoughts that we learned about uh, in the last video on internal energy and the first law of thermodynamics, in particular the energy balance. So what we're going to finish out on in particular is flow work and what that even is, and how and why it distinguishes itself from the rest of the guys. And this is the topic to me that was always the hardest to grasp, and because it just didn't make sense fundamentally to me. They like to give these examples on and I'll show you some of those examples. I just find them to be wanting on using pistons. But we're going to talk a little bit in depth. I'll give you three different ways that, from easiest to hardest on how to understand what flow work is and how that ties in finally into the derivation or the definition of enthalpy. So, and what you'll find out, hopefully at the end of this, is that enthalpy, Gibbs free energy, in particular, those two, which are going to be the most useful terms that you'll have. Moving forward, or terms of convenience. So a term of convenience being that you can try in your head as hard as you want to be able to derive some meaning to some of these variables, but it's a term of convenience in that it doesn't necessarily have a strict a vocabulary definition, so it's not going to be like everybody likes to give like these fruity definitions of entropy. It's a measure of disorder, or Gibbs free energy. It's the energy useful for work, or enthalpy. It's the real internal energy. Sometimes people say, or sometimes people say it's energy. It's the energy of the molecules plus the energy to keep it, the universe from collapsing in on it, on that control volume. I don't like any of those. I really find them to be wanting. I find their definition to be better served based on what they're used for. So you'll see what enthalpy is used for very quickly at the end of this lesson. So moving forward, this is where we left off. We had a rough definition of the energy balance, looking at the inlet internal energies, kinetic energies, potential energies, minus the outlets, plus the net entering Q from heat, and then entering shaft work from some rotating shaft. But it could be a variety of things. And we didn't talk about expansion or compression work, which is not included here because most systems don't, that are steady state systems, don't have that. But we're going to talk about that in depth too as we move forward. And then we have the plus at the very end in yellow, plus flow work in minus flow work out. So what is flow work? So let's look at the first and simplest way to understand it. So flow work is not energy, right? It is work. So that's the first thing, is that there's a pure energy form and there's work. Remember, work has units of energy, but it's more representative of a change in energy, right? You're doing something to change the energy, right? So flow work, in the first and easiest way to understand it, is to elaborate on the Bernoulli principle. All right, so what did Bernoulli say? So let's look at his example. Bernoulli had an example where he had a pipe at one elevation moving up to a pipe at a different elevation of a larger diameter. This is the most classic example. And he looked at the pressure, the velocity, and the height at each of these different points. So we'll say this is height 2, it's height 1. Obviously, we're going to have velocity 1, also velocity 2, and pressure 2, and pressure 1. And he was looking at an incompressible fluid, meaning the density was constant, but it doesn't necessarily matter. But what he found was that the pressure plus velocity, 1/2 of the velocity squared, plus the gravity time the gravitational constant times the height is going to equal a constant. In other words, it also equals P2 over rho plus 1/2 V2 squared plus GH2. So what this is indicative of is that somehow or another, the kinetic energy term here, in the kinetic energy term, I'm going to draw an arrow and make it look a little messy, but up here, they're more or less identical. They are identical. So, and similar with the gravitational term. So, it would stand, in the logical mind, you would say, well, this must be the internal energy term. It's not. Don't worry about that just yet. But what even is the pressure divided by rho? Well, in terms of units or variables that we use in thermodynamics, we don't like to use rho very often. We prefer to use volume. And you might say, why would we use volume in this case? Well, rho is going to be equal to, let's see, what units do they have? Let's just look at those. Well, it's going to be in kilograms per cubic meter in SI units, which so happens to be the exact inverse of volume in units that we use in thermodynamics. So that means P1 over rho is going to be equal to P1 volume. Again, that's specific or molar volume. So taking this into account, that means we're going to have P1V equals 1, not equals, but plus 1/2 V1 squared, velocity 1 squared, plus GH1 is going to equal a constant. So this term here is what we like to call flow work. So way 2 is going to be looking and examining the situation, or at least Bernoulli's law you could think of by looking at the power input to the system. Again, Bernoulli he got to the point where he figured out that the product PV is somewhat interchangeable between the kinetic and potential energies, right? So we need to understand, is PV a pure form of energy, or is it a form of work? So we called it work. We've already said where we're going, but what we want to do is hammer down the principle that it is in fact work and not internal energy. It's not kinetic energy. It's not potential energy. So let's get specific here and define work. So we're looking at a change in energy over change in time, which is equivalent to power. So, but what we're going to look at is the power input, right, to the system, to the control volume, right? That's what we're wanting to calculate. And we do it at the inlet. So let's draw our example here. So we have a tank. It's got a pipe coming in. And this is our control volume here. So this is where we're doing all of the we're wanting to do the analysis on this control volume. And right here we've got a pressure, we've got an area, we've got a velocity. Right, it's and that fluid is moving, right? Obviously that's the velocity into the control volume, right? So it's having to overcome pressure in order to do that, right? And that pressure that it's overcoming is P1. So let's go ahead and define power. Well, what is power? So power, as it's always been, the work rate, right? So that is the rate of change of energy, right? So you could also define it as the change in work over change in time. Well, we know from general physics that work is going to be equal to, and we're going to go ahead and put the subscript 1 there. It's going to be equal to F dx, so a force times a distance, right, divided by the change in time. to get to the power term. We know that the force at the inlet is going to be equal to the pressure at the inlet times the area of the inlet. Therefore, stepping it in, we get pressure, area, dx1 over dt. And we know that from general physics again that dx1 over dt is just going to be equal to the velocity term. So that gives you PA1 down to V1. Now we know, again, from just logic, that the area times the velocity is going to be equal to the volumetric flow rate. So finally, we're at PV, but not quite PV, not the PV we need. What we can do with this is pretty straightforward and get it into the V terms that we need. Again, we want V in specific terms. So what we can also do is just multiply the specific term by the volumetric, or the mass flow rate, and we end up with the same volumetric flow rate, right? So that ends up being and now, so we've got power equals the mass flow rate times P times V, times pressure times volume. Specific volume, again, but it's pressure times volume. So that's the second way we've done it, and that's kind of the easiest analytical way to get to the work being done on the control volume. Right, and we know it's work done on the control volume because it's the pressure that the fluid has to overcome at the inlet, at the very entrance of the control volume. Right, so that's the amount of energy that's having to go to actually push the fluid across the fluid boundary, the control volume boundary. Now, way 3 is a stricter, I guess, derivation. We'll call it the formal derivation, and there's a wrong way to do it and a correct way to do it, and I got stuck for years on the wrong way to do it. So I'll try to be very brief with my explanation on, and kind of maybe I'll start with what the wrong way to do it is. So the wrong way to do it was to say, okay, I know what work is. Again, work is going to be equal to, let's say, d work over d time. It's going to be equal to force times the distance, right? So, let's take a look at that a little bit deeper. I was trying to, when you look at it the strict way, is figure out what is this dx is. So everybody, that teaches it wants to say, it's a differential distance from here to here. And that's not true. And why that's not true is because this force, which we know, again, is pressure times area, it's not constant. Even if area 1 and area 2 is constant, and this is x1, x2, the pressure 1 and pressure 2 is not constant. We know that because of, you probably haven't had fluid flow yet, but we know that dP over dx, equals, at least in turbulent flow, it's going to be equal to 2 times the fanning friction factor, V squared, over D. And that's definitely not linear. Or it is linear, but it's not. It means the pressure does change. And what we got in the above example was a constant pressure, right? The pressure of the inlet only, right? So we can't use the pressure, this derivation, and in my opinion, it's the wrong way to go about it. So how do we do it then? Well, we do it by looking at, we'll go restart way 3. It's the formal derivation. Well, again, it's kind of similar to the power derivation, is that what you think about is this fluid, and it's a column of fluid that flows through it over a time dt. And that over that time dt, it's going to travel dx, right? But what you're looking at it is from the reference point of the inlet only, right? So the dx is actually the distance is representative of maybe the volume that you've actually pushed into the control volume, right? So you've pushed a volume that looks like this into the control volume, and this is your dx here. But the pressure of that volume is not a function of dx. That pressure is constant. There is no function of pressure across that dx. So it's because really, again, the x of analysis is not changing. You're looking to understand how much force is actually being pushed into the fluid from that point forward, right? I know that seems a little bit hand-wavy still, but that's really what you're trying to analyze, is how much force or energy is actually being exerted at this point. And what is its power, right? So again, to go down to that derivation. So again, in order to look at that derivation, we're looking for how much fluid was passed through that orifice over delta time, and how much energy did that require to do that, right? So you're looking for how much energy you actually it took to push that fluid into the control volume. So let's make a couple charts here and see if we can hammer this out. So first off, let's have a force chart. All right, so we're going to call this force. And the good thing is, in this case, force is constant. All right, force is constant because at the inlet, it's going to be equal to the P times the A. And we'll have a delta time right here. And then the next graph, we're going to have the volumetric flow rate. So that volumetric flow rate, it's also going to be constant because that's the assumption here. The assumption is that the volumetric flow rate is in fact constant. And that's going to be equal to the area times the velocity, right? Which ends up being, area 1 dx1 over dt. All right, so let's make another chart. And this chart's going to be equal to looking at the force times the differential x. Well, again, this guy's constant, right? Because he is going to be equal to F times dx. It's going to be equal to P A V dt, which is going to be equal to PV dt, which equals PdV, right? And again, let's go ahead and make sure that I mark all this as delta t's. And then a final chart to show the integral to where we get work. What you'll see is the first ever diagonal but straight line, where over that time, delta t, we had the total amount of energy added, or work, is going to be equal to PVT. So from a formalized definition version of this system, again, we're looking for the work rate, so we would then take the derivative of that with respect to time, right, and then arrive where we did at power. We can now finally derive our equation for the energy balance. So what we have is the differential change in internal energy over change in time is going to be equal to the mass flow rate in times U1 plus P1 V1 plus 1/2 V1 squared plus GH1 minus M2, again, U2 plus P2 V2 plus 1/2 V2 squared plus GH2, representing all of the energies. Let's move this over a little bit so we can fit in our last two terms, plus the rate of heat input and the rate of work input. Because the U1, P1, V2, H2, H1, all those are just plain terms and not of a differential basis, it's often written as such. Now this term here is a very particular term. Again, we talked about this before. It's a term of convenience. We like to group flow work with internal energy into a single term, and we like to call that enthalpy. So enthalpy is going to be equal to internal energy plus the product of the pressure and the volume. Right? And again, the pressure and the volume is not a form of energy, it's a form of work. So again, enthalpy is a term of convenience and does not represent a form of pure energy. It does in part in the internal energy part, but it mostly, is a term of convenience. So, again, we'll rewrite this and say that dmu or dt is going to be equal to negative delta m for the mass flow rate times the enthalpy plus the kinetic energy portion plus the potential energy portion plus the heat rate plus the work rate. Now, in a steady state system, the term on the left goes to 0. So let's go ahead and copy this to have a final little aha moment here. Move on to the next page. All right, so our final aha moment is going to say, let's break this up into the steady state version. So the steady state version looks like this term being equal to 0. So when that term equals 0, we get the mechanical energy balance. This goes to say that delta m h enthalpy plus 1/2 the kinetic energy term, right, plus the potential energy term is going to have to be equal to the heat input plus the shaft work. Now, finally, also, let's assume that it's in fact a closed system and not a steady state system. So a system in which it's just a box. So for a closed system, so let's say open system at steady state. And we'll say this is a closed system at unsteady state, or not in steady state. Well, that would imply that the mass flow rate term goes to 0, right? So the dm also can be pulled out, right? So then you get m du over dt must equal the heat input plus the shaft work. Now, I'm going to caveat this term right here. We stopped at shaft work because we did not consider closed systems. In real closed systems, we often look at engines. So those are not necessarily, the shaft work is not the only type of work that the control volume can experience. It can also do compression or expansion work. So we'll actually summarize it as just plus the work rate. And that's all she wrote, guys. If y'all liked that video and you found that helpful, please like, comment, and subscribe. Thank you.